Hello, everybody. We're about to get started on our webinar here. For those, well, I guess you probably know who I am. My name is right here on the screen. For those of you that do know, my name is Brady O'Leary. You might have seen me listed as Braden O'Leary. I'm one of the co-founders of Triple Point Environmental, and I'm currently one of the general managers as well. I've been working with wastewater lagoons pretty exclusively since 2008 or so. So quite a bit of lagoon experience. Today, we're going to be continuing our Lagoon Masterclass. This is track 3, module 1, and it's titled Meeting an Ammonia Limit at your Lagoon Ammonia Limit. That's the most important thing. We're meeting the ammonia limits at lagoons. So this presentation is one of my favorites to give. I've given it quite a bit, and it's because lagoons are, I would say, they have a Dr. Jekyll and Mr. Hyde personality when it comes to ammonia treatment. Lagoons are fantastic at BOD treatment. They're fantastic usually at ammonia treatment in the summertime, sometimes even through fall, sometimes in spring. But you'll find that a lagoon that kicks butt at treating ammonia 9 months of the year does a terrible job at treating ammonia, sometimes treats no ammonia in the wintertime. That's because lagoons simply weren't designed to treat ammonia when they were originally installed. Most of these lagoon systems were installed after the Clean Water Act in the 70s. They didn't care about ammonia back then. We care about ammonia now. So they weren't, like I said, they weren't designed to treat that ammonia. And in the cold weather, excuse me, in the cold weather, the bacteria that are there to treat the ammonia don't have the right conditions to reduce the ammonia to acceptable levels to the EPA. And that's what we're going to be talking about today, the conditions under which certain kinds of bacteria will treat ammonia. And what's interesting about bacteria is when you give it the right conditions, it can do pretty amazing things. Again, if you've seen my webinars before, you've probably seen or heard this story rather, but I love it. It comes from Jerry Shell, one of the kind of the founders of wastewater aeration and oxygen transfer. He told us a story where if you give bacteria the perfect conditions for treatment in your wastewater lagoon system, let's take a heterotrophic bacteria and say the perfect conditions for that heterotrophic bacteria are the perfect food, we'll say cream cheese, and they have all the conditions they need for digestion. They have the right N and P ratio, they have all the oxygen they need. How fast can that bacteria eat cream cheese? That's pretty fast. So let's say this entire earth, the chair you're sitting in, the desk in front of you, or the couch that you're on is cream cheese. Okay, and we have, let's suspend the laws of physics because I don't know how physics works if the entire earth is cream cheese, and say that around the earth is the perfect conditions for bacteria digestion. I take one heterotrophic bacteria, put it on the tip of my pencil here, and I drop it on my webcam. And it divides and eats and divides and eats. And again, it's got the perfect conditions, so it's just going to keep dividing and eating. It'll divide and eat through the webcam, through my screen here, through my desk, through the room, through the entire earth. How long do you think it will take for that bacteria to consume the entire cream cheese earth? And usually when I'm in a presentation and I get answers, people are like, oh, a year, months. And the actual answer, somebody eventually gets it, is 72 hours. And in the last hour, half of the earth is consumed in that last hour. So this is equal parts a demonstration of like the law of exponential numbers, but it goes to show bacteria are really powerful things if we give them the conditions that they want to continue digestion. So we're going to talk about how we do that for ammonia in your wastewater lagoon system today. Let's get my mug out of here and carry on. Like I said, this is part of our Lagoon Masterclass. This is something we've been doing for some time now. We're really excited about it. And we cover all sorts of topics important to your wastewater lagoons, including lagoon process, biosolids, lagoon hydraulics, algae and duckweed, data analysis, troubleshooting. We have a whole series with the thought behind this being, if somebody who has zero experience or very little experience with wastewater lagoons can come and take our multi-track course, our master class, and come out knowing more than 99% of wastewater people about this specific topic about wastewater lagoon systems. Today, specifically, we're focusing on nitrification. So I've already done an introduction. We're going to go over the nitrification process, the process under which we nitrify or we reduce ammonia. We're then going to talk about the 8 reasons why lagoons kind of stink at nitrifying or removing ammonia. And then we're going to have a discussion, or like hypothetically, let's say your state, wherever you're sitting right now, is imposing a limit, and states are doing this on different timelines. I'm going to have a limit in 2026, for example. What do I do now? And I think our recommendation here is learn about it, study up as part of what this presentation's here to help provide. We also want to help you understand your limits and then help you to understand your options. What do I do if my lagoon is not able to hit the limits that I'm being given by our regulating bodies? What I'd like to do here is take a step back. In college, I was at least partially a philosophy major. So I always like to ask, why? Why do we care about ammonia? Why do I care about 10 milligrams a liter coming out the back end of my plant? My lagoon treats BOD from 300 down to 30. Why do I care about 10 or 15 milligrams a liter of ammonia? Well, the first answer is ammonia is very toxic to fish, and we're discharging often to rivers and streams, sometimes with pretty low flows. And humans can handle a little bit of ammonia. Our livers will help to digest it. Fish don't have that ability. So even at low concentrations, fish growth can be impaired and fish could be killed. Also, it's toxic to amphibians, different crustaceans. We're putting a pollutant into rivers and streams where other things live, and those things don't like to live with ammonia. That's pretty straightforward. This isn't the major reason, but it is a reason. The more important reason is that we're not just putting your wastewater into rivers and streams. We're concentrating the wastewater from wastewater lagoons around the nation into these kind of point source locations. As you can see here is the Mississippi watershed. It's kind of the biggest example in the United States where all the wastewater discharged to rivers and streams in this part of the country, we'll say a third of the country or more, is being discharged to one location in the Gulf of Mexico. And this is contributing to massive pollution acutely at these locations. So what we have down in the Gulf of Mexico, you may have heard of it, it's called a dead zone. And there are dead zones like this worldwide, where essentially they're called dead zones because nothing can live in these areas because of how polluted they are. So it's not just your 10 milligrams a liter, it's 10 milligrams a liter from everybody around you as well. And if you notice, that Mississippi watershed is about right here, which also correlates with kind of the epicenter of where the wastewater lagoons are in the country. These little dots, every one of these is a wastewater lagoon, and this is just municipal. This isn't even talking industrial. There's a heck of a lot of lagoons in this part of the country. So let's say that the Mississippi watershed is has one third of all wastewater facilities in it, and I think that's a very conservative estimate. And many of these are also facultative lagoons in this part of the country, which means they don't have any treatment at all. So they're discharging pretty much all of the ammonia that comes in. I wanted to get a sense of how big of an impact this actually has. What does this dead zone look like? You tell me it's a dead zone, what does that mean? So let's talk about it. That dead zone is about 80 miles across. So if you're in Louisiana and you want to go catch some shrimp, you got to go 80 miles offshore before you can catch anything meaningful. Everything in this red area is pretty much dead. This area is called, it's subject to what's called eutrophication, which is a Greek word for essentially means overfed. What we're doing is overfeeding this part of the country with ammonia. Ammonia is a fertilizer, and we're overfeeding algae that lives in the Gulf of Mexico. So we're essentially hyper-fertilizing this algae to the point where you can barely see through the water, and this algae actually suffocates pretty much all other life out in that part of the country. And that's because at night, algae, they stop producing oxygen, they switch their respiration, they start consuming oxygen, which means that, like I said, we're choking out the dissolved oxygen in this part of the country. So how much algae are we growing? I can't picture algae. So I did some math. I said, okay, if every one of these lagoon systems is discharging their ammonia for 3 months of the year, in the cold months of the year, that's about 300,000 pounds of ammonia that we're dumping into the Gulf of Mexico. I was like, okay, well, that means nothing to me. I can't picture 300,000 pounds of ammonia. So then I said, okay, if ammonia is a fertilizer, if I can visualize something else, how much algae can we grow with that much ammonia? I couldn't get any real metrics on that. So I lived in the Midwest for a long time. We know how much corn we can produce with that much ammonia. So I just said, okay, let's say we're growing corn, we're not growing algae. We can grow 145 million tons of corn with the algae we're putting into just the Gulf of Mexico. And then yet again, I'm like, well, what does that look like? I can't picture that. So I said, okay, let's say we harvest that corn, just take the cobs, not the husks, not the roots, none of that other stuff, just the cobs, put them into train cars. How long would that train be? And that train would go around the earth 2 times. So imagine a train that long, just cart by cart, going down to the Gulf of Mexico and dumping corn in there. That gives you a sense for how much algae we're growing and how big of a problem this really is. This is a huge problem, and this is why the EPA and local regulating bodies care a lot about how much ammonia is coming out of the back end of your lagoon system. So what do we do about it? We're going to go through the nitrification process here. And to start, the nitrification process is we're trying to get rid of ammonia to begin with. Ammonia comes in NH3 or NH4, or it's either ammonia or ammonium, depending on the presence of an ion. Is it in the water? What's the pH? For all intents and purposes, we'll call these two ammonia. It's a colorless gas. It stinks. If anybody has a cat and that cat is not the most, we'll say it goes to the bathroom places that it's not supposed to go, that smell of cat urine is it's primarily ammonia. And ammonia is part of a bigger collection of nitrogen compounds. So I wanted to talk about those because people get these confused a little bit. And depending on where you are in the country, you might have one of these or multiple of these on your permit. So I wanted to go through the different forms and categories of nitrogen. We've already discussed NH3, NH4, ammonia, and ammonium. We'll just call these ammonia from a treatment standpoint. Other parts of the ammonia process or nitrification process will produce nitrite or nitrate. And then you also have organic nitrogen, and this is nitrogen bound up in the cell walls of living things. It could be an algae, it could be bound up in a protein from an industrial food processor. Essentially, this is nitrogen that's difficult to get to. These are the primary subcategories of nitrogen. Altogether, these equal TN, or total nitrogen. On the left side of the screen, ammonia, ammonium, and organic is TKN, or total Kjeldahl nitrogen. Took me about 3 years to learn how to say that word. On the top side of the screen is total inorganic nitrogen, TIN. This is what we love the most. And if you're a regulator out there, we can treat pretty much all of the TIN out of a wastewater lagoon system. It's the organic that's a little sticky because that's nitrogen that is protected. Again, it's bound up with a protein. It's in an algae cell, and that algae cell doesn't want to be consumed, so we can't get to that nitrogen. So if we're talking about what we can meaningfully impact in a wastewater lagoon system, the subcomponents of TIN are that. So how do we remove this ammonia from our wastewater? We do it with a process called nitrification. Nitrification is we convert ammonia or ammonium to nitrite and then eventually nitrate. And this is done by a couple of different bacteria, but we call these bacteria nitrifiers. Nitrosomonas and Nitrobacter are the big ones that we rely on. And this is where the Dr. Jekyll and Mr. Hyde nature of wastewater lagoons comes in, is because the kind of bacteria that do most of the heavy lifting in wastewater lagoons, like the BOD eating bacteria, these are heterotrophs. I call these things tiny little terminators. They are the reason lagoons are so reliable, consistent, and predictable. They grow really quick, they outcompete other organisms, they get what they want when they want it, and they're simply reliable. On the flip side, the kind of bacteria that do nitrification are very specialized. They don't eat carbon for their food source. They can actually eat nitrogen or fix the carbon out of the atmosphere for the carbon that they need. And then they can eat specialized things like ammonia, but they're specialized, but they're incredibly fickle. They are slow to mature, they're hard to grow, they can't compete with the terminators. And they have a whole bunch of conditions that they want to do their job, and they don't want to work for anything. So getting those conditions right in your wastewater lagoon system is the key to getting your lagoon system to nitrify the way that the regulators expect it to. So we're going to talk about those key factors. What do those nitrifiers want? And how do we give it to them in a lagoon environment? And in some cases, maybe if you're down south, we can optimize 1, 2, 4 of these factors in your lagoon system to improve nitrification, maybe to a place where you are hitting your limit. Can I modify our existing lagoon to hit those limits? And in the event that you can't, let's say your lagoon is too challenged, it's in a part of the country where nitrification is just simply not going to happen on its own in a lagoon. How do I evaluate the best solution to guarantee nitrification in the future? Can I drop something in my lagoon? Can I add some process to my lagoon system to guarantee nitrification for some future effluent limit date? So let's talk about these factors. The first factor nitrifiers want is plenty of oxygen. Nitrifiers use a lot more oxygen than the heterotrophs do to consume what they consume. Like for example, BOD eating bacteria will consume about 1.5 pounds of oxygen to treat 1 pound of BOD. The nitrifiers, by comparison, need 4.6 pounds of oxygen to treat just 1 pound of ammonia. So 3 times more air to respirate to treat a pound of something. At the same time, these nitrifiers don't want to work for it. They want a dissolved oxygen content available right around them of 4, 5, 6 milligrams a liter. They don't want to have to work to breathe. Heterotrophs, they'll rip 2 oxygen molecules off of a nitrate molecule if they need air, because they're going to get what they want. These nitrifiers are like, nope, I want it to be super easy. Most lagoon systems are not operated at 4 or 8 milligrams a liter. Some operators are trying to save a couple bucks, and they might be operating their lagoon at 1.5 DO or 2 DO. And that's not an ideal environment for nitrification. Nitrification will be severely hindered at DOs that low. So the idea is, if you are looking to nitrify, having higher DOs, especially later in your lagoon system where nitrification typically takes place, is important. And also, mixing is essential. If you put all of this oxygen in one part of your pond, usually it's in the front part of the pond because people think that's where the BOD is, that's where we need to put the air. Then that oxygen is not mixed all the way to the tail end of the system. And like I said, nitrification is going to take place at the tail end of the system where there might not be air and there might not be mixing. Now, the next factor the nitrifiers want is a low presence of BOD. Like I was saying earlier, you have the heterotrophs, kind of like the terminators. The nitrifiers I compare to the princess and the pea, where there's one thing that's not right, they're not going to do they're going to complain. A few things are not right, and they're simply, they're not going to work right. If you put the terminator and the princess and the pea in a room together and said one of you survive, terminator is going to survive, 100 times out of 100. Basically, the terminators will actually eat the nitrifiers if given the opportunity. So what we have to do is get the BOD down such that there's a lower presence of heterotrophic bacteria in the lagoon system. So generally, this is going to happen in your lagoon system where the wastewater is between 20 and 30 milligrams a liter of BOD. And at that location, there's just not as much food for these heterotrophs to live, and the nitrifiers can start to thrive. Another thing the nitrifiers care about quite a bit is pH and alkalinity. They're quite sensitive to these. They want roughly a neutral pH. They can go a little bit higher, the 7, 8, 9 pHs. Definitely do not like it on the more acidic side of things. The optimal pH for nitrification is around 7.5 to 8. This is not a problem for most municipal plants, not a big deal, but if there's a strong industrial component in your lagoon system, something to consider. Another thing to consider is alkalinity. So the nitrifiers, they require alkalinity as a part of the nitrification process. For every 1 milligram a liter of ammonia that we need to treat, we need around, I think it's like 7.2 or 7.4 milligrams a liter of alkalinity. And if the alkalinity is not present, nitrification will just stop dead in its tracks. This is not a problem, I would say, at 95% of the municipal plants around the country, but there are some plants in different regions, whether they're mountainous regions, or there could be, we've encountered a couple of towns that actually reduce alkalinity as a part of their potable water treatment. And that was actually starving the nitrifiers in the lagoon system down the pipe. So take a look at your alkalinity. Do I have 7.2, 7.4 milligrams a liter of alkalinity for every 1 milligram a liter of ammonia I want to treat? One of the bigger reasons why nitrification doesn't happen as reliably in wastewater lagoon systems is what we call nitrifier mass. What does this mean? What this means is we can't get enough of these bacteria out there to do the job. Like I said, they're slow to eat, they're slow to grow, they're slow to mature, they're just slow. So if they're slow, we need a ton of these out there to get the job done that we need to get done. And the difficult thing in the lagoon system is that these are attached growth organisms. They can't just grow in the water column and tumble around like the tiny little terminators can. They have to grow on something. And the problem with the lagoon system is it's designed to be one big volume. There's not a lot of surface area for these things to grow on. And they move so slow, we need more than we can grow in a lagoon system. And this is pretty crazy. You look at a lagoon system here on the screen. This is DeSoto, Iowa. It's about 5 acres. It's 167,000 square feet of liner surface area where these bacteria can grow. Sounds like a lot, but they're so slow that at DeSoto, this lagoon system could not treat their ammonia to proper effluent levels with the equipment, with just the lagoon system they had. So one of the questions is, how do we get more surface area to grow these bacteria in our lagoon systems? This is probably the biggest factor in why lagoons aren't the best at nitrification, and it's temperature. These bacteria like to be warm, above 60 degrees Fahrenheit. And once you start dipping below 60 degrees, you'll find that nitrification drops off quite a bit. Below 40 degrees, it does continue, 40 degrees Fahrenheit, around 4 degrees Celsius. It does continue, but at a rate that's so slow that it looks like nothing's really taking place. And we see this year in and year out at lagoon systems, where the temperature is this green line here. Obviously, temperature goes up in the summer, it goes down in the winter, at least in this part of the globe. And when the temperature goes up, the ammonia effluent, this blue line, goes down. We can get some pretty good ammonia effluents at wastewater lagoon systems, between 1 to 3 milligrams a liter, pretty reliably, at least if it's designed to do that when the water's warm. But as the temperature comes down, you'll find that the ammonia in the effluent spikes right up to above 10 milligrams a liter, and it's countercyclical. Every summer, ammonias are low. Every winter, ammonias are high. This is simply because, again, the bacteria slow down. One of my guys here at Triple Point, Tom, was comparing it to like molasses rolling downhill in the winter. It'll do it. It happens really, really slow. It's like a glacial pace. Another factor, number 6, for nitrifiers to do their job in wastewater lagoons is what we call bug basics. This is just making sure your lagoon system doesn't have anything toxic out there. There's not any biocides, heavy metals, industrial cleaners. We have a lot of municipalities that will take industrial waste, and these industrial plants will do cleaning in place processes in the middle of the night, and they'll put quatamines or some other industrial cleaner down the pipe at 2 in the morning, and all of a sudden the lagoon system changes color, it starts to stink, the ammonia effluent goes up. So having an understanding of what toxic components we could be putting in this lagoon system, what are they and where are they coming from? Because these will affect the heterotrophs, the tiny little terminators, but nowhere near as much as the princess and the pea kind of bacteria. Like I said, they're super sensitive. Another key factor is sludge, and this is kind of a sleeper one. And this is a pretty complicated screen here, so you don't have to memorize. There's no test on this. But this is a lagoon schematic that was given to me by a facility in Ohio, and I love this one. And the operator said, he was talking to me and said, "Hey, what's going on in my lagoon system? Take a look at this." And he showed me that the ammonia coming into his plant right here, 6 milligrams a liter. And then next cell it's 11, next cell it's 12, next cell it's 22, next cell it's 28. At the outfall of his plant, it's 34. This guy's lagoon system is an ammonia production machine. And he's like, what is going on? Why is this happening? And I took a look at this and I was like, wow, you have a lot of sludge out there. And the operator is like, no, no sludge, just had it removed 2 years ago. Yeah, no sludge. I'm like, no, you definitely have some sludge. I can tell, because of the ammonia production here. And come to find out, when they drained the lagoon system, he's like, yeah, we had about 7 feet of sludge, 8 feet of sludge. We did not know that. The reason I knew that he had sludge is because of a phenomenon called benthal feedback, where what happens with the sludge is, in the sludge is undigested organics. There's a high volatile component of the sludge, and those organics are breaking down slowly through anaerobic digestion. And when they're broken down through anaerobic digestion, some byproducts can be created. And you might have seen this in a lagoon system with lots of sludge. You might have seen some H2S, some rotten egg smells. You might have seen methane, some bubbles coming out of the bottom of the lagoon. What you also find is production of ammonia. So sludge breaking down anaerobically can actually put ammonia into your system. And this is super important because we can treat 100% of your ammonia in your plant, but if it goes to a next cell that's got 4 feet of sludge, that's now putting ammonia back into your water, it doesn't matter how much we treated, because that last cell might be taking your ammonia effluent to a place where you're going to breach your effluent limits. So understanding your sludge and how volatile it is, how much is out there and where it is very important. I know that we have other masterclass modules on sludge specifically. Sorry, 1 second here. Okay, moving on. The last factor we're going to be talking about today for nitrification is flow. And this is kind of a sidebar issue, but it's important to mention in wastewater lagoon systems, is that we need to make sure that the water's going where we want it to go. If we have HRT in our lagoon system, or hydraulic retention time, we're expecting the wastewater to be sitting in one lagoon for 10 days, and it's only sitting there for 2 days. That means we're only getting 20% of the treatment we originally counted on. So we need to know that we're utilizing our infrastructure as it is designed. So if I can give you an example, here's a lagoon system where we had some aeration we put in, and it wasn't working the way that we expected. The effluent was not tracking to what the model would predict. So we took a look at it, and the influent's supposed to be right here, and the effluent is this little nub right here. And we, after a couple of rocks turned over, we said, okay, let's do a dye test. Is there something going on with the flow in this lagoon system? You'll see the green dye, when put into the influent chamber, does not come from over here. It pops up first right here, and it shoots right up, and then you'll notice it beelines it for this little nub, which is the effluent, within 2-3 minutes of it going in the water. What's happening is the water is short-circuiting from the influent to the effluent of the lagoon, and the bulk of this lagoon was not being used, at least to its fullest potential. And this happens in lagoon systems all the time. So, like I said, if you are having treatment issues in your lagoon system, make sure that short-circuiting is not a common problem. A bit of a recap here: why lagoons fail to nitrify. It could be the presence of too high a BOD, the wrong pH, or not enough alkalinity. Could be toxins. Generally, municipal lagoons do not have a problem with these things. The reason that lagoons generally stink at nitrification is because we can't get enough of the bacteria out there to get the job done. The temperature might be too cold at least sometimes of the year. Lagoon might not be designed with enough oxygen from a pounds standpoint, or it might not be run or operated at a DO that's amenable to these bacteria. The oxygen might not be mixed throughout the entire basin. There could be short-circuiting in the lagoon system, or there could be sludge. These are very common reasons why lagoons fail to nitrify. And if you're an operator and you have an effluent limit of 10 milligrams a liter, and your effluent's very commonly 11 milligrams a liter, you can go out there and change a few of these things and probably get below, that 10 milligram liter you need to get to. So again, ask yourself, is my lagoon optimized or designed to treat ammonia to give these bacteria what they want? And if not, how can I tweak it to do that? I think it's also important to understand your limits. And you can talk to your regulator, you can talk to your local rural water folks that can help you with this. but not every limit is the same. How strict is it? Is the limit in milligrams a liter? Is it a concentration, or is it in pounds per day? And there's a big difference there, because pounds per day might be designed to be a limit at your design flow. Your design flow might be 1 mgd, and you're allowed to put in so many pounds per day. But if you're operating at a fraction of your design flow, maybe 0.2 mgd, then the amount of pounds you're putting into the discharge pipe could be significantly lower. So keep that in mind. It's not just around design, it's around what am I actually putting into that river or stream. What times of the year do I have a limit? You'll see some states are imparting stricter limits in the summer because they know lagoons can do a better job when the water's warmer, and more loose limits in the wintertime. So does my lagoon have a problem nitrifying when the limit actually applies from a time of year standpoint? Can we change discharge time? Like we have, for example, controlled discharge lagoon operators. I've seen them that will actually hang on to their wastewater all winter long. They'll store it because they know the nitrification isn't going to take place. And then when the wastewater starts to nitrify in the spring, when that water warms back up, that's when they start to discharge. They hang on to it when the lagoon's bad at nitrification. Another question is, can I change a discharge location? I've seen plants that are discharging 80 feet right by their plant to some river or stream that looks like it's only passing a gallon a minute. It's barely moving at all. There's going to be very strict limits on that kind of stream because the wastewater impact on it is very large, proportional to the flow. But these same plants, they could pump. This one example I'm thinking of had the option of pumping about 400 feet away to a very large river, and the limits from the regulators for them to discharge to that river were significantly higher than having to discharge to that little stream 80 feet away. So can I discharge somewhere else and have more lax limits is the question to talk to your regulator about. And like I mentioned earlier, can I meet the goals that I'm given with lagoon that I have as it stands? If not, can I tweak a few of these factors? If I can't do that, if it looks like I cannot accomplish this limit might be 2 milligrams a liter, and I'm in somewhere in Montana. I'm sorry, if you have a lagoon in Montana and you have to hit 2 milligrams a liter, you're not going to do it by adding a little bit more DO. It'll help, but it won't guarantee nitrification year round. So I guess the question is, what do I do from this point to get to where I need to be? And that's what we're going to be talking about here for the remainder of this presentation. What are your options at that point? If I can't tweak something, I got to add something to my lagoon to get this job done. What does that look like? And what's kind of interesting about this is all these different ways of, especially the guaranteed ways of treating ammonia in your wastewater lagoon system, they do the same sorts of things. They're building food with the same kind of ingredients. They just do it a little bit differently. And I kind of liken it to like Taco Bell. If you think about it, Taco Bell only has like 8 different ingredients. They just layer them differently with different quantities to create different products. But again, the ingredients are the same. You're going to find that's the same with these nitrification options. And the reason that the ingredients are the same is because all these different technology options are addressing at least the majority of these key factors that these nitrifiers want to get them to do what we want them to do. We're going to talk about 4 very common methods. So in lagoon media, there's a bunch of companies that do this, from Entex, Webitat, Triple Point has one of these. There's attached growth rock filter. A couple companies have done this, but the big company that's doing this is Nexum with their Sager. There's cover and complete mix. This is generally seen by, I think, a company called Lemna does the cover and complete mix. And there's temperature regulated MBBR. This is primarily what Triple Point does, but there's a few different ways to skin the cat here, and we're talking about how these differ. We're going to, I kind of want to get this one out of the way quick, and then we'll go to the other 3. And the reason I want to get this out of the way is I think in lagoon media, there's a bunch of companies that are doing this, is a great solution for some municipalities or some industrial plants, but it's not a blanket solution nationwide. And we'll talk about why. So what in lagoon media is you can see a couple different models here, this is drop-in media. And you could hear media as surface area that bacteria can grow on. We're just putting a lot of surface area out in the lagoon because the lagoon doesn't have the surface area we need to grow the bacteria to treat the ammonia. So we drop in what are essentially like bacteria condos or hotels into the lagoon system. Most of the different technologies will have some kind of aeration system beneath it to make sure the water is mixed through these bacteria hotels, and also the DO is there for the respiration to take place. They generally sit in the bottom of the lagoon system. And the idea here is the lagoons will settle out the sludge, lagoons will treat the BOD, media will be placed with the BODs low, so there's not the competition from the heterotrophs. They are aerated underneath. They do not control for flow. The kind of one of the downsides of media is you've got a media block here, you've got a media block there, but there's water space in between. Not 100% of the wastewater is going through these devices, so it's not going to treat 100% of the ammonia in these lagoons, at least in cold weather. So they are short circuit vulnerable. They do have a lot more nitrifier mass than a lagoon because there's a lot of surface area in these blocks. There's a medium amount of nitrifier mass. And from a temperature standpoint, they don't really do anything about temperature. They're placed at the bottom of the lagoon where the water might be a little bit warmer. But other than that, they don't address temperature. So what we see for in lagoon media is that it's good for light limits, and it's also good for warm weather compliance, where temperature is not an issue. If you're down south and you're trying to scrub off a few milligrams a liter of ammonia, drop-in media is a great option. But generally what we see in colder climates, here's some data from a company in New York. The red line is the ammonia effluent. As you can see, ammonia effluent high in the winter, goes down in the summertime, and then when the water gets cold, they have a hard time treating ammonia again. In 2001, they installed right here some in lagoon media, and you can see the ammonia precipitously dropped. The in lagoon media did a great job, especially in the warmer months, of treating down to well below 1 milligram a liter. But you can see as the water started to cool off a little bit, it wasn't as dramatic as over here, right? The in lagoon media is doing a better job than no in lagoon media, but as the water cools off, you can see the effluent jumps back up to what is above most wastewater lagoons effluent limits at 15 milligrams a liter when the water's cold. And when the water warms back up, it drops back down. So like I said, this is kind of a supplemental solution or a certain parts of the country solution. This is not a blanket nationwide solution. Next, let's take a look at, this is a more, I consider one of the more comprehensive approaches. This can work pretty much anywhere in the country. This can work in Canada, this can work in the Arctic Circle. The next 3 devices are going to be that way. Kind of I want to guarantee nitrification no matter what, no matter where I am, no matter how challenged I am. It's because these next 3 technologies address more of what the nitrifiers want. And like I said, when I give the nitrifiers what they want, they will do what we expect them to do. So this is an aerated rock filter, and the company that does this, said Nexum does this, they put in, it's a rock filter, right? They put in a ton of rock, a very certain specification of rock into this large basin here. This basin is always outside of the lagoon system because they want to make sure 100% of the flow is going through and every drop of water is being treated. And then rock is used as attached growth surface area where bacteria can grow. This company does the same thing. They will let the sludge settle out in the lagoon. They'll let the lagoon treat BOD. They do aerate underneath the rock to provide the bacteria air to respirate. They control 100% of the flow. And what they do with the nitrifier mass is they do not, they say, okay, we know this bacteria is moving like molasses downhill in the winter, but it's still moving. We're going to put so much bacteria out there that no matter what, we're going to kind of brute force treat this wastewater. And essentially, we're compensating for low temperature with just sheer number of bacteria. So these reactors can be pretty good sized. As you see, there's a human down there. They tend to be about 10 feet deep. Could be a quarter of the size of a football field. And they're just going to say, okay, we are treating no matter what the temperature is because of all the nitrifier mass that we have. This could treat pretty reliably down to non-detect if you wanted to, no matter what the temperature. Another approach, this is more of like the Lemna approach, is cover and complete mix. And it's a bit of a different philosophy. So the philosophy is, we're going to settle the solids out in the lagoon system in a settling pond. That's pretty standard. But instead, they are going to rapidly treat the wastewater in the lagoon. And that's because it's known that around the country, wastewater is going to come in from the influent around 55 Fahrenheit, 60 Fahrenheit. That's warm. That's pretty warm. That's warm enough for nitrifiers to do their job. Not perfectly, but they will do their job at that temperature. So this approach, this cover and complete mix approach, is how do we maintain the temperature of that water, treating the BOD as fast as possible to get those competitive heterotrophs out of the way, and then putting it through a reactor on the tail end to nitrify, because we want to maintain the temperature from the influent. So what they're looking for is rapid lagoon digestion, and they do that with generally a higher mix kinetic rate, often a complete mix cell up front with aeration, extra mixers to get the wastewater treated not in 20 or 30 days, maybe in 5 or 10 days to maintain that temperature. And that temperature is also maintained with the cover at the surface. The flow is then put through an external reactor on the tail end. So 100% of the flow is put through this reactor, or you might see it over here. And inside of there is media inside the reactor to polish off the ammonia, because the bacteria attached growth, they're going to grow on that media. So instead of compensating for low temperature, this approach is maintaining the temperature that comes into the wastewater lagoon and treating the wastewater as fast as possible. This system can also treat to low limits year-round, pretty much anywhere you are. One of the challenges of this is it's a lot of equipment and kind of reinventing the lagoon with a lot of mixing and a lot more treatment. And there's a cover to add as well, but very reliable on the effluent. Next, we're going to talk about a temperature regulated MBBR. This is generally what triple point does. And you'll see that we're addressing the same kind of considerations, the factors those bacteria care about, in a slightly different way. Similar to the other technologies we've discussed, sludge is settled out in the lagoon system. We let the lagoon system treat the BOD down to that 20 or 30 milligrams a liter. And then we aerate an external reactor where 100% of the water flows through. And this is where we get a little bit different though. What we do is we say, okay, nitrifier mass is really important. We need to get a lot of media out there. We put a certain kind of media in these reactors that has a huge surface area given its volume. So we have a highly concentrated nitrifier mass. And the point here is the more concentrated the nitrifier mass, the smaller the reactor we can create. Another thing that we do is, instead of compensating for temperature, instead of maintaining temperature, what we do is we optimize temperature for nitrification. So you can see here what we have is a reactor on the inside. It's some aerators to provide oxygen. And then what we do is we put little pieces of media in here, millions of pieces of media, and keep them in with these screens on the inside of these reactors. And the media is where we grow the bacteria. What we also do is we have a immersion heater, you can see it right here, where we heat the wastewater. And this sounds kind of crazy, but this is why we're talking about optimization for nitrification. Here's just a top-down look of what it might look like. These reactors are generally about 3 or 4 hours of retention time per tank. We heat the wastewater with either electric immersion heat. We do this in most lagoon systems because they're small. This is like, if you know anybody that has a saltwater fish tank, it's essentially the same sort of immersion heater, but on an industrial level. For larger plants, we might do a boiler and heat exchanger. And the reason that we do this is we know that nitrification happens very reliably down to about 4 degrees Celsius. Below that point, it becomes very unpredictable, and we have 2 choices. We can make our reactors 5 times the size to compensate for temperature. We don't like to do that because that means you're buying 5 times the equipment for a temperature your lagoon might only see for 6 weeks of the year. Or we can maintain the temperature at that 4C and above and keep the reactor as small as possible, keep the capital costs as low as possible. And that's where the heater comes in. We're not heating a hot tub from 32 degrees Fahrenheit to 105 degrees Fahrenheit. We're heating water from what's usually in a lagoon system around 36 degrees Fahrenheit to 39.5 degrees Fahrenheit. So it's just a little touch of heat to keep it in that sweet spot for these bacteria so we can get 100% nitrification no matter what, and keep the size as small as possible. We do cover these reactors to make sure the heat's maintained. I'm not going to go into the details of the BTU calculations, but if the water's coming in at 41 degrees, it'll come back out at 40 point. It loses less than a degree of temperature across the continuum. So we keep the temperature that we put in the wastewater. So what we do is we control the biomass, and we do that with little pieces of media. As I mentioned, we put millions of these into the reactors, and collectively these have a huge amount of surface area. What's interesting about the way that we approach this is that we don't have to use standard media, which has big holes in the middle, because standard media is used at wastewater facilities that are treating heterotrophs, so the tiny little terminators, which create a very thick, mucousy, gelatinous biofilm. And the purpose of standard media is they have big holes because they don't want these to plug with bacteria. Since we're growing the nitrifiers that are much finer bacteria, and we can take advantage of that finer bacteria by having smaller and smaller holes. And what you can read this as is more and more surface area in the same volume. Standard media might be 500 cubic or square meters of surface area per cubic meter. We can get 900, sometimes more square meters per cubic meter, because we're not afraid of these holes plugging. Long story short, we can pack a lot of bacteria in a small space. And that small space is really small. If you remember earlier when I pointed out DeSoto, the 5 acres of surface area, that huge area where they couldn't get the job done with all of that surface area out there, we can replicate that same surface area in an 8x8 cube. So a very high amount of bacteria growing on surface area in a very small space. What we've also found is that the heat is not required 100% of the time. The heat's only required when the water dips below 4 degrees Celsius, also at design flows. And what's interesting about this is wastewater systems are designed generally for about a 20-year lifespan. So we're thinking about how big our town might be, how much loading we might have in 20 years, and designing for that. That means when we start it up on day one, it is way, way, way over capacity, at least in most cases. And overcapacity means the water is moving through these reactors slower than it would at design flow. So what we're finding is that our lagoon operators only need to heat the wastewater when they approach their design flows. When they're way over capacity early on, they don't have to turn the heater on at all. So our philosophy here is, why build a system that's 5 times the size to compensate for temperature for a design flow that our town might never get to? Why pay for that now? What we say is, turn the heater on, pay for it when you need it, when your town grows to that point, when you have a larger taxable base, instead of paying for it up front. The aerators are removed from the surface. I'm not going to get too far into that. So what's the difference? And it kind of goes back to that ingredients conversation we were having earlier. It's the same ingredients. These different technologies are addressing media or surface area, aeration, flow, BOD, etc. Same bacteria across all technologies is doing the same work. They just implement it a little bit differently. And I guess the question is, why do people implement it differently? I can say from our perspective, the reason we like to go with these thermally regulated reactors is simply size. Here's a design from an engineering firm that did a comparison between us and an attached growth rock filter, or the Nitrox MBBR and an attached growth rock filter. And the Nitrox can fit in this area right here next to these lagoons. This is in South Dakota, an equivalent system with an attached growth rock filter, because they're compensating for temperature with size, took up a significantly larger area. And at least in this application, they would have had to require some additional land to get that done. So this is why we like to control temperature, and this is why we like to have a very fine media. From a timing perspective, I'm going to skip this guy. Here's just another example of shear size. Let's get to the nerdy stuff. I love this stuff. So we wanted to do some additional research on nitrification. And this whole conversation we're having today is, if we give bacteria the right conditions, how impactful can they be? And we wanted to evaluate that with what we did as MCA, or microbial community analysis. And essentially what we did is, it's an RNA, it's kind of similar to like DNA, an RNA analysis where we took some media, scraped off some of the biomass that grew on that media, and put it into a test tube with some acid. And what that acid does is it breaks down the RNA strands of the bacteria that we put in that tube. And scientists, with their magic, I can't tell you what they do. They put it in some probably $1 million machine, but they do it. They can evaluate all those RNA samples in that vial and tell you exactly what kind of bacteria are growing in that biomass. Really, really neat. So we did that. We took one of our pieces of media, scraped off some of that black goo, put it in a tube, and we got the results back. And it was really interesting. Usually what you see is like Flavobacterium. These are like the tiny little terminators, is massive, like through the roof, 10 times more than any other bacteria. It surprisingly is not one of the highest. If you look at some of the highest, Nitrosomonas, as we talked about earlier, one of the nitrifiers, is off the charts. And generally, Nitrosomonas looks like some of these other bacteria here. It's just a small blip. And it kind of goes to show that when we give these bacteria what they want, we can grow the right kind of bacteria in huge concentrations. So here's another look. So this trunk line here shows where the higher populations of what bacteria are in the wastewater. So you do have, where is it? Flavobacterium. I'm not seeing it. You do have the heterotrophs in here. They're still present, just not present in a massive concentration. This is actually the wrong. This is the wrong photo. Well, that maybe we can come back to that during the question and answer because this is not correct. But what we see in the actual data, you know what? I'm going to pull it up. I got a minute. This is just a different presentation. We're going to run through here. I love this graph. Here we go. And marketing is going to be unhappy with me for showing a different presentation. Sorry, guys. Okay, here it is. The thicker lines show, as I said, where the most bacteria are. Like I said, you do get Flavobacterium and some other heterotrophs down here, but the thickest line goes all the way up to cold adapted nitrifiers right here. Nitrosomonas, really, really exciting. What we actually calculated was that we have 10 times the predicted amount of nitrifiers from a typical plant in these reactors. Again, it goes to show you give them the right conditions, they're going to do what you want them to do. And here's an example of that. This is DeSoto. I've shown you this a few different times. We've worked, this is actually where we started to develop the technology, starting back in 2010. When we started, we needed to prove that we could do what we said we wanted to do with these reactors. And we did a pilot with the Iowa DNR. Put the pilot right there. I'm not going to go over the data. You can see the pilot unit right here. We brought the DNR to come see it. It was a 2-year pilot. Pilot was very successful. The DNR approved it, and we put in a 2 treatment train reactor here with 4 tanks. This is DeSoto from the top down. In Iowa specifically, 50% redundancy is required. So instead of 2 tanks, 2 big tanks, we had to put a dividing wall down the middle, so half the system could be taken offline. Some states have that requirement, not all do. And here's it in operation. This is the first winter. We also did some aeration as well, but as you can see, the reactors are pretty small, able to shoehorn it in on land they owned right here. But the data is what we're here to talk about. So as you can see, the BOD, TSS were pretty noisy before startup at the DeSoto plant. Again, we also did the aeration, so we were taking care of the BOD as well. I just want to highlight real quick the ammonia effluent. You can see that in this column right here, that first winter. So 0.1 is the non-detect level. So we can't measure below 0.1, at least the lab that they dealt with cannot measure below 0.1. And you'll see pretty reliably, the ammonia was fantastic the majority of the winter, with 2 outliers. Got an asterisk here and an asterisk here of 8 and 5.1. And the reason that the ammonia spiked at this location was that the contractor was doing sludge removal of the later cells in the lagoon system, kicking up sludge, which if you remember is kicking up some of that benthol feedback ammonia into the water column, and that spiked the ammonia on the effluent. So kind of a demonstration of sludge can be a real problem sometimes. But outside of those two excursions, you can see the ammonia that summer averaged 0.4 milligrams a liter, and the ammonia that winter averaged 0.78 milligrams a liter, well below the 2.8 milligram a liter ammonia limit that first year. But that was just the first year. Like I said, these bacteria are slow to grow and they're slow to mature. So we'll look at the next year in a second. That first year gave us a really interesting look because they had what was called the polar vortex. And if you lived in the Midwest, this is plastered all over the news, where wind chills were -50 Fahrenheit, temperatures were in the -20s Fahrenheit for a couple of days. Super, super cold. About as challenging of an environment that you can get for nitrification because of how cold it was. So we begged the operator, hey, will you please, Daniel, will you please take a sample? He said, yeah, sure, but I'll have somebody else do it because I don't want to do it myself. Dan, I don't know if you're on the webinar, but sorry for putting you on blast like that. He had his coworker, Nick, do the sample for us. Nick went out, took a sample, and it was 15 milligrams a liter going into the reactor. You see that right here. And the effluent coming out of the reactor was below 0.1. This is the non-detect level. And it just goes to show that because we controlled all the factors for nitrification, including controlling temperature, we were able to guarantee nitrification in conditions equivalent to the next ice age. So pretty exciting stuff. That next year, when the bacteria were more mature, we turned the heat off. Absolutely no heat was used the next year. And the effluent was even better than it was the year prior. And you can see the ammonia effluent in this column right here. 0.1, 0.1, 0.16. The average for the entire winter, that next winter, was 0.18 milligrams a liter. Like I said, well below their effluent limit of 2.8 milligrams a liter. And like I said at the top of the call, bacteria are amazing when you give them the right conditions to thrive. And that's the goal with these different wastewater technologies that we're putting into lagoon systems, is how do we address these 8 factors that these bacteria care about to optimize nitrification for my lagoon. You can do it a few different ways with a few different technologies, a few different companies, but the important thing is giving these bacteria what they want. And when we do, the results are pretty fantastic. If you're really hungry for more and you don't want to wait for that next masterclass, please take a look at our Lagoon University, where we have webinars just like this, on demand, accessible whenever you want. So just check out lagoonuniversity.com. These are very educational. We're not trying to, shoot fish in a barrel, trying to do salesy stuff. What we want to do is get education out there. What we realized is there's not many sources for education for wastewater lagoon systems. There's no centralized group that's educating operators around the country. And operators, they might meet fellow operators at different trade shows or talk to neighboring towns, but there's not a steady flow of information that they can leverage to help operate their lagoons better. We're trying to do that with Lagoon University. So take a look if anything, any of these interest you, and we're adding new content all the time. So let's get to Q&A here. Happy to answer any questions. Please type them into the little webinar box here, and Eve will pass any of those on to me. In the event that we cannot answer all of your questions today, or if you have a question that pops in your head in the middle of the night, please feel free to shoot me an email. My email's on the screen right here, brady@lagoons.com or braden.o'leary@lagoons.com also works.
Hey, Brady, I have a couple questions.
All right, let's do it.
The first one refers to your slide showing the Benthal feedback from the plant where the ammonia was higher coming out than coming in. Could you tell which sludge had the most in it of the series? It looked like the ammonia doubled across the cells.
Yeah, there were some cells that have more ammonia production than others. And what you're going to find is it's going to be in cells that have 2 things. One, a larger quantity of sludge. 5 feet is always going to be worse than 1 foot because there's more sludge out there, coupled with the amount of volatile solids in that sludge. You can take a sample, and this is a webinar for another day. You can take a sample of the sludge, test the VSS, and the VSS, we'll say the solids of the sludge might be 30,000 milligrams a liter, and the VSS might be 15,000 milligrams a liter. That means you have about 50% volatile solids in that sludge, which means that is the portion of the sludge that can be feeding ammonia into your system. So like I said, how much is VSS and how much in total volume do I have can give you which is the bigger offender of ammonia production in our lagoon systems. Or you can just do what that schematic did for us, is get out there and do intrapond testing. Test between cell 1, cell 2, cell 3, cell 4, however many cells you have, and figure out where is the ammonia coming from. And that can also point to the offending sludge without actually getting out there and poking around.
This next one, and you'll like this, and there's actually a full webinar on the subject. Can recirculating sludge and wastewater from later quiescent cells back to a primary aerated cell help improve ammonia treatment in a cost-effective way, rather than upgrade aeration throughout?
In general, recirculation is fantastic for a number of reasons. I'm trying to think of the ammonia impact. TN impact, absolutely. So when you're recirculating, what you're doing is you're taking kind of veteran bacteria from the back end of the plant and reseeding them up front. You're also taking high DO water, because usually later cells have less BOD. They tend to have a little bit higher DO, not always, but they can. So the DO of the cell 3 might be 6, and the DO of the first cell might be 1. By recirculating high DO water back, you're bringing free oxygen back to the front of the plant. You actually might lower your aeration needs on the front end. You're also bringing nitrates back, and nitrates are an oxygen source for the heterotrophs on the front end. From an ammonia treatment standpoint, I don't think it would significantly improve NH3 treatment. It will do TN though, because like I said, we're bringing nitrates back. Nitrates are a component of total nitrogen. And if you bring them back to the front end of the plant and they go through certain parts of your pond, most lagoons are partial mix or not aerated at all. That means there's going to be anaerobic portions of the pond. When those tiny little terminators go anaerobic, they want oxygen, and if they can't get it around them, they'll go to that nitrate molecule, which has 2 oxygen molecules on it. They'll rip the oxygen molecules off for them to breathe, and then the only molecule that's left is N. N is a gas, nitrogen is a gas, and it'll off gas into the atmosphere. So recirculation is a way to reduce TN in your lagoon system. I might be thinking about this incorrectly from a nitrification standpoint. We'll get back to you if I'm wrong, but I don't think it will help with nitrification specifically.
What are the benefits of a floating baffle? Flow control, short circuit protection, medium for growth?
So, I mean, technically a baffle is, yeah, surface area for growth for sure. Bacteria will grow on it, nitrifiers will grow on it. I wouldn't say it's a cost-effective way of getting surface area out there, but it will slightly increase nitrification. But the other points you make are true. Flow control is the big one. Baffles, I love baffles. And if you ever looked at a lagoon system, have you ever asked yourself, like, why is it always 2 cells? Why is it always 3 or 4 cells? Why not just one giant lake? And that's because different cells, or adding a baffle is kind of a way to emulate different cells. You're separating water from other bodies of water. Functionally, they're the same thing. What you're doing is preventing the water from beelining it from the influent to the effluent. Water is always going to take the path of least resistance. It's, you know, if we'll say, you know, this is a lagoon system right here, right? We'll say influence up there, effluence down here. The water's not going to come in and be like, hey, I want to go hang out over here, and I want to go hang out over here, and hang out over here. It's not going to do that. It's just going to say, I know where the effluent is, and the water is going to go directly for that. If we put a baffle in here, and we require the water to come down, come around this precipice down here, go up and maybe around another baffle over here, you force the water to go on a more tortured path. You hold it back. It's actually, it helps your lagoon be more what's called plug flow, which means we're controlling the flow and the water's moving through it more like a pipe instead of beelining it for the exit. For every baffle you add, you'll increase the treatment performance of your lagoon system by about 15% for at least the first few baffles. That's a lot of improvement on BOD and ammonia treatment, simply because we're preventing, you know, a molecule of BOD from finding its way to the effluent before it's had a chance to be eaten.
This will be the last question. Any subsequent questions we'll answer after the webinar. We're about out of time. Can nitrifiers ever exist in the water column? they prefer attached growth, but are they exclusively attached growth?
I'm sure there's some PhD in the audience right now that's going to send me an email about why I'm wrong in this. But I don't believe they can grow in the water column. They need something to grow on. That being said, there's stuff in the water column moving around. These are partial mixed lagoons, which means solids are mixed. So they will attach to solids that are floating around a water column. Also, some lagoons, we have designed a few lagoons to be complete mix. Complete mix lagoons have essentially all solids that come in that are not like a grit or a rock or a stick are kept in suspension. And when they're kept in suspension, that means the solids are always exposed to bacteria and oxygen, and a flock can be formed in the lagoon. If you have a high mix environment, the nitrifiers can grow on that flock. Most lagoons aren't operated that way, but it can be done. Actually, the nitrifiers can sometimes grow on heterotrophs, technically, even though they're kind of a competitor. But like I said, you don't see that often. Most lagoons are operated under a partial mix regimen, which means most solids are settling out at the bottom, and the water just doesn't have a lot of stuff to grow on. And with that, I believe I have given the giant hook on the stage by Eve. That's the end of our presentation. I appreciate everybody for coming. Like Eve said, we'll happily answer any unanswered questions in an email a little bit later. Appreciate you coming to the webinar. Like I said, if you have any questions, feel free to reach out. I appreciate you all for coming, and thank you, Eve, for putting it on.